Welcome, everyone. I see we have some familiar participants, but for those who don't know me, I'm Julia Stegman, Professor of Environmental Engineering at UCL and Director of the Interdisciplinary Circular Economy Center for Mineral-Based Construction Materials. Our center, funded by UKRI, it consists of 25 academic co-investigators from 7 host institutions, collaborating with more than 50 external stakeholders. And so we're in our first year of operation with 4 years of UKRI funding and have been spending this year gearing up for the first 7 of our 15 postdoctoral research projects, as well as various academic and industrial engagement activities. So today we're delighted to welcome you to the first of a series of lunchtime seminars on subjects relevant to our network of current and prospective collaborators. The seminars will be constrained only by the theme of our center, enabling the transition to a circular economy for construction minerals. And we expect that they will stimulate discussion of a wide range of issues of academic, industrial, and societal interest with speakers from all disciplines and all parts of the supply chain. For our inaugural seminar today, we are honored to present Dr. Wendel Sebastian, who is Reader in Structural Engineering at UCL. And Wendel joined us 4 years ago by way of Bristol and Cambridge. While he's not a formal investigator for the center, Wendel's research very much intersects with our activities with plenty of scope to collaborate, as has already been the case in one of the activities that he's going to be telling us about. So the plan is for Wendel to speak for 20 minutes, which will be followed by 10 minutes of questions and discussion. I invite you to put your questions in the chat as Wendel is speaking, but we'll be prioritizing questions where people raise their hand and speak to ask their question at the end of the seminar, and then be coming back to the chat since we don't have that much time. So with that, I will introduce Wendel, if you can put up your slides and tell us about your work.
Okay, thank you, Julia. Okay, so I think I go to share screen. There you go. Yes, can everyone see this?
Yes.
Okay, excellent, thank you. Thanks a lot, Julia, for the introduction. Good afternoon, everyone. I appreciate your joining this session. As Julia indicated, I'm an academic with a keen interest in understanding how structures, and in particular low carbon structures, behave in response to load, and very importantly, in translating that understanding into design guidance for use by practitioners. So if we start with a sort of brief history, I think many of us will agree that stone and timber are probably amongst the oldest construction materials. And there are countless examples of bridges, buildings, and other types of structures made out of stone and timber, which have withstood the test of time. Some of them have lasted centuries, possibly even millennia. And when the Industrial Revolution came around, of course, there was a shift in emphasis from stone and timber essentially to concrete and steel, which are fantastic materials because they're very stiff, they're quite strong, they can be quite durable when they're well protected. And for steel in particular, there is that very useful property, ductility, which engineers rely on quite a lot. That's the ability to stretch without breaking when it gets to its strength. And then after quite a while, after the Industrial Revolution, more recently, climate change, quite rightly, has come into very sharp focus. And we've been looking at various ways in which the construction industry can decarbonize. And one of the very important ways of doing that, of course, is reusing our construction materials. This is a theme which the very nice network project that Julia is leading will be developing some groundbreaking ideas for, feeding into the circular economy. It also means that looking again at the materials, timber and stone, becomes important because they're such low carbon materials. One of the things we need to pay attention to, of course, is making sure that any new low carbon materials we come up with have very good quality control so that they can match the levels of confidence that we've developed in steel and concrete. And for example, with timber, of course, we've got engineered timber, cross-laminated timber, glulam, and so on, in which select slices of the material with minimum defects in there are actually brought together, fastened to each other, glued together to give us components that can have a behavior of, or exhibit a behavior as consistent as we get for steel and concrete. Before I launch into the low carbon agenda itself, can I just say that, of course, structural engineers have a dual role in the fight against climate change. On the one hand, we're basically looking at designing our existing infrastructure and our built environment against the effects of climate change. These two images relate to a project that I've been working on in the Caribbean with the World Bank. On the left side, we can see very clearly an aerial view of a bridge which has almost been demolished by the large logs which have been swept downstream by the floods, which are becoming more intense, which are becoming more unpredictable in terms of when they occur and the frequency with which they occur. And on the right-hand side, what we can see here is an example of a simple scheme that engineers have been designing, which is an upstand here on the upstream side of the bridge, right next to the bearings, which of course are of key importance to try and minimize the impact of these logs. We can't prevent them from being swept downstream, but we can try to minimize what they do to the structure. The other thing we are finding is that it's not just the in-service stage which can determine what type of structure we use. What we're finding is that because the floods can often come during construction, it means that anything like the use of props on the riverbed to support the weight of wet concrete during construction can be an unwise idea. So effectively using steel beams that are clear of the riverbed to support the weight of the wet concrete can actually be quite important. And therefore it means that construction stage considerations with climate change involved can be governing the designs that you come up with. Here is another example of something we've been looking at, which is basically airport roofs. This time we're not talking about floods, we're talking about hurricanes. And indeed the hurricane wind speeds and pressures are exceeding the category 5s, which have been designed in the codes of practice. And so it means that new forms of roofing, you know, not just the cladding, but also the fastening of the cladding to the structure below becomes quite important. And the definition of the tests that you need to make sure that that system of the cladding and the fasteners behave properly in hurricane winds. So representing the hurricane wind force effects very well in the test is an issue that becomes quite important. Okay, so in terms of a decarbonizing strategy, the obvious thing is to go for low carbon materials. Quite often though, in many floor systems, walls, buildings, and so on, the most effective and most efficient structures tend to rely on combinations of the different materials. So you might find that quite often you're using a new low carbon material with an existing material. So for example, concrete, low carbon concrete with an existing steel. And because you're connecting the different materials, the connections themselves become important as the components made out of the materials themselves. As structural engineers, we have to make sure we understand not just the immediate response, the short-term response to load, but also the long-term behavior. What happens when under its own self-weight, something's been sitting there for a while, you've got a lot of moisture, you've got a lot of change in temperature. Those are the sorts of things we need to be looking at. And bearing in mind that the construction industry is standards driven, we need to make sure that our understanding translates into design guidance. So on the left side, I've deliberately put this image there because there's a sort of multi-level, a multi-stage process that we have to go through. We need to understand the materials. Then we need to understand the components made out of the materials. And then we need to understand the entire structures themselves. And to that end, an example of a project that we've been working on, which has been led by MACE and which is funded by Innovate UK, can be seen here in two key images. On the left, you can see very clearly a two-story mock-up, full scale, which has been built by Mace at Brandon, about 2 hours drive north of London. And in essence, what we've got here are these cassettes, these modules, which are 9 meters long, almost 3 meters wide, made out of cement-free concrete, which I think is supplied by DBG Holdings, connected to steel beams. And one of the key issues we've been looking at there is how can we create connections between the concrete slab and the steel beams that are reversible? So exactly the idea that Julia is looking at, can we make these dismantleable so that if we want to transfer them from one construction site to another, it shouldn't be difficult, but at the same time, the structural integrity of these components remains intact or remains at a very, very high level. So we don't have to do too much work to actually get them back into service again. And one of the things they were looking at here was how easy is it to construct? What can we improve on in terms of the, the connections, the details that hold the different bits of the assembly together? This is one very promising form of low carbon construction, which we are looking at with industrial partners. Another example is, and again, the theme of prefabrication comes in, is timber concrete composite floors. One of the prefabricated modules you can see on the bottom right here, there are similar spans and widths to the ones that we've been looking at. And the idea is that you remove a lot of the concrete that you would otherwise get in a reinforced concrete floor. So, and you basically replace it with some very lightweight timber components underneath. By removing a lot of the concrete, you actually reduce the weight quite a lot. So it means your foundations, in theory, can be much less concrete intensive. The overall structure is cheaper. We're using less ordinary Portland cement. So it means that we can actually, contribute to the decarbonization agenda. And again, the whole idea of putting in connections that enable us to be able to separate these components again, if we need to, for whatever reason, in particular to reuse at another structure, that is actually an important part of the research that's being conducted. And the whole idea of prefabrication actually enables that. There are various schemes, including precasting the slab units and leaving holes in them so we can put our connectors in, and equally we can take them out later on. We've got to make sure, of course, that the connections remain robust. So if we do this a few times, the integrity of the connection between those different components doesn't drop. So understanding the long-term structural behavior of those reversible connections is quite important. Web Yates engineers, whom we've been collaborating with, actually designed and supervised the construction of a 5-story building, which you can see on the left here. It's very close to King's Cross, and this building actually houses the Anna Freud Center, which is a charity looking into the welfare of children. UCL actually collaborates with the Anna Freud Center a lot, and indeed UCL have been utilizing the space in this building for postgraduate teaching and research. On the top right-hand side, you will see that evidence of the fact that I like to involve my MSc and PhD students. Here we are basically performing the same sort of human loading tests on the floor, one of the floors of this building, the timber concrete floors, before it was actually handed over to the clients. And I'm again pleased to say that the response was very good. I think between us, we weighed something like just over a ton. So we stood and then we jumped, compared the results, and those results were quite encouraging. Okay, yet another structural form. On the left side, I don't need to introduce the iconic St. Paul's Cathedral. St. Paul's has been around for over 300 years, and again, it's testament to the durability and the strength of stone. On the right side, we are working again with Web Yates and some other industry partners to see how we can actually use pre-stressed stone for floor systems. Of course, if we're using them as beams, we need to press the stone blocks against each other. Pre-stressing, of course, is something that's been developed for concrete. And one of the important differences between concrete and stone is that with concrete, you start the material starts life wet. So it basically means you can pour it into molds and put various shaped objects in there to facilitate what you want to do with the concrete, and in this case, to facilitate the implementation of the pre-stressing process. Stone, of course, is exactly the opposite. It comes already hardened, and therefore there are different challenges involved in actually implementing the pre-stressing process. So we cannot simply take the process which has been developed from concrete and transfer it to stone. We have to adapt the concrete pre-stressing process. And that is one of the areas that we are addressing, alongside actually working out the detailed structural mechanics of these stone structures. Indeed, yet again here, one of the themes we've been trying to address is how can we make this reversible? There are certain schemes in which the best way to go about things is to actually glue the pre-stressing steel to the stone. But of course, if you do that, it becomes very difficult to make it reversible. If you don't glue, there are other ways of actually transferring the force between the steel and the stone, and that facilitates, of course, the whole idea of reversibility. So in many ways, the theme that Julia is leading with this wonderful project is a theme that we're also grappling with. And I imagine at some stage in the future, there's going to be a convergence between our activities and the high level work that Julia is actually spearheading. The final example that I want to share with you is on the use of fiber polymer composites. These, of course, are materials in which you combine high-strength fibers, quite often carbon or glass, with resins. And the resins can be epoxy, vinyl ester, polyesters, and so on. The materials people have a very good handle on this. The properties you get, the mechanical properties, depend on which fibers, how much of the fibers, what directions you put the fibers in, as well as the type of resin that you use them with. And these materials have a very good track record in a spectrum of applications, some of which we can see here. So the renewable energy industry, the marine industry, the automotive industry, and indeed the sort of aerospace people have been using these materials quite successfully for quite some time. And that basically has encouraged the civil engineering structures people to try to apply these materials in bridge applications. So here are two examples of bridges which were recently built in the UK using this technology. On the right-hand side, the entire bridge was made as a single unit. So the manufacturing method is clearly quite advanced. This bridge is 13 meters long, and it's basically being floated up the Thames, where to its final location, where a crane, a low power crane, would have lifted it into position. On the left, you see another bridge, 2 lanes, almost 10 meters long, made entirely out of this fiber composite materials. This is near Bristol, where I was before, as Julia mentioned. And in both cases, the low weights of these bridges, because the materials are very highly, their stiffness to weight and the strength to weight ratios are high, but also you make sort of voided structures out of them. So that reduces the weight further. So again, your foundations are cheap, but also because they can be prefabricated and they're very light, you can build them at a factory or assemble them at a different location, simply transport them to site and lift them into position over a very short possession period. So that means delays to traffic and the emissions you get from vehicles which are sitting in traffic are minimized considerably. In addition, because these materials are meant to be quite durable, the idea is that hopefully during the life of the bridge, and in the UK, bridges are meant to have a life of up to 120 years. With composites, we're roughly probably at the stage of about 50 or 60 years, which is still pretty good. But the idea is during that period in service, there should be minimal need to actually inspect them or maintain them. It doesn't mean it should be zero, but it means that it should be minimal. And in addition, if there is a need to maintain, one of the issues that is important is again Julia's theme, which is effectively reversible connections. Remember, these are modules that we are bringing together. And if the connections between the modules can be reversible, it becomes very easy to take a part of the structure out and replace it with a new module. And if this can be done very quickly, while retaining the high structural levels of integrity of the overall assembly, then it means we've got a low carbon solution which inhibits, again, vehicle emissions while the structure is in service. So my last main slide here We've been working with industry, with national highways, with county councils who own bridges made out of this fiber polymer composites to basically test them in situ. So alongside laboratory testing, I think that there is a role for field monitoring, especially given that sensors, which we can get remote measurements from, are actually cost effective. They're quite reliable, so the readings are repeatable, and they're quite durable. So a lot of developmental work has gone into sensors for exposed applications, which basically means we ought to be able to sit at the offices and pick up a lot of data on how things are behaving, whether it's wet and icy or it's warm and humid. On the left side, this is some work we were doing with South Gloucestershire Council, using their gritting lorries loaded with grit. I think they weighed about almost 30 tons, running back and forth singly, in tandem, and we were taking lots of readings from sensors that are well hidden within the structure. On the right-hand side, repair of the structures, because inevitably, as I said, there will be a need for this. How do we repair in a way that is reversible? What is the effectiveness of repair? And this bridge is located in Oxfordshire, and we were asked to collaborate with Oxfordshire County Council and National Highways to install some sensors that we are still using to assess the effectiveness of the repair method, which itself was pretty good. So getting that sensor data, linking it to laboratory testing, and actually interpreting the results in a way that can be translated into design guidance is important. We did this using the results from these two tests. We actually fed our understanding into an updated guidance, which was produced by Highways, or National Highways, last year. Having said that, although there is a focus on using the new materials, I mentioned before that the ductility of steel, which is this ability to sort of stretch when it reaches its strength without breaking, is hugely important. So I think a lot of future solutions will need to look at getting reversible connections, feeding into the reuse agenda, involving steel with the new low carbon materials and concrete as well. That's going to be quite important, because that ductility is going to enable us to embed some important safety features into the structure. We never know exactly what's happening in a structure which is in service, and that ductility acts almost like a fuse. Whatever we are not exactly sure about, if something does happen, that ductility allows the structure to remain safe, and for us to have more confidence in the designs. So on that note, I hope I've given you a flavor of some of the different decarbonizing solutions that we've been looking at with industry. Watch this space. We'll be very keen to feed the results out into the wider industry and to continue to collaborate with academic colleagues, and to do that through networks, for example, the one that Julie has very nicely set up here. Thank you very much.
Thank you very much, Wendel. We don't have any questions in the chat at the moment, but please do raise your hands if you, or you can still put questions in the chat, but please do raise your hands if you'd like to ask a question. While people are thinking, I actually had loads of questions. I thought it was a very educational talk for me, Wendel, because I'm not a civil engineer, and for instance, I never knew that you could pre-stress stone. So that's actually fascinating. Oh, I see Thea has a question. So we'll go with Thea before I ask my question.
Thank you, Julia. Hi, Thea.
Hello. I introduced myself a bit earlier. So I come from, I'm a research fellow in the centre, looking at how regulation and standards can help us move towards greater circularity. And what you're presenting does require a great amount of addressing of standards, and the regulation is sort of reconsidered around use of secondary materials, obviously meeting sort of risk requirements for subsequent use if we've got circular by design, obviously specification standards and things like that. And one of the big questions I have are regarding the pace at which this regulatory and standards revisions need to occur, where do you see the bottlenecks on your side in terms of communicating with industry and with government to actually achieve the revisions that are needed?
That's a really good question. Thank you, Faye. I mean, if we look at this sort of spectrum of materials that we're thinking about, I mentioned, for example, everything from stone to timber to composites and so on. Each of these are sort of materials that behave differently. They behave differently from concrete and steel and from each other. And one of the issues is, you know, if you leave them around for a while, how do they perform? Because the long-term behavior might be different from the short-term behavior. I think, you know, inevitably, especially because it is very easy to beam information on a new product and a new idea around, you know, from one end of the part of the world to the other, it becomes, I think there is probably an understood culture of, you know, we want to know now how the thing behaves, and then we move on to the next thing. And that, to a certain extent, is maybe slightly at odds with the fact that quite a lot of the time we have to wait a long time to know exactly how these things behave if we want to build a bridge that lasts 100 years, for example. And quite often, by the time the information is out there, you know, we've just tested the concept and the results are quite promising. And typically people state that, you know, they don't try to conceal that. And then the implicit understanding is that it's over. But in fact, we need to apply them in certain situations. So for example, I know over the years, people have tried to apply, for example, fiber composite bridges in the middle of the countryside, where probably the traffic isn't that heavy. And then after a few years, there's a sort of sense that it's behaving well. Let's try another slightly more involved application where you've got more traffic. So suddenly 6 years later, you might see the same news, you know, about the same type of technology with a few advances appearing. And I think one of the issues, to answer your question directly, is that we need to make government departments, governments and so on aware that when these technologies emerge, there is still an element of development that needs to occur. And therefore, we need to be looking probably 15, 20, 25 years ahead, because the long-term element of it is quite important. And of course, if you get a change of government where you have a different set of priorities, suddenly something important drops off the agenda. And one of the things I think we need to do is to try to secure, you know, agreements that, you know, whomever is controlling the purse strings continues to recognize, for example, that this is something that needs continued investment. And I think that time scale element of it is one of the things that we need to pay attention to. There are ways of trying to get around this. You were previously talking about, you know, tests in the lab and, you know, people try to do accelerated testing, for example, Faye. The issue is, I think if we do something with a lot of moisture, with a lot of a high temperature and so on, translating that into a reality where something is sitting, it gets rained on, sunned on for a third of the time, and then it might get snowed on for another 10% of the time. And this will happen in different ways over a 20-year period. It can be a bit of a challenge actually translating those laboratory results into the reality. So I think laboratory testing is going to be okay, but it does need to be complemented by long-term monitoring. And therefore we need people to be patient, to recognize that there are going to be different stages in development. And I think that's one of the reasons that the concrete industry has been so successful, because they've invested quite a lot in this sort of long-term element of understanding and improving their product. And indeed now with climate change, there are various things that the concrete people are doing to decarbonize the material because they understand it so well because of all the investment that they've made in it. It would be good. I think there's a sustainability element. I think that's the term. Sustainability in research, sustainability in the material. It's actually not sustainable if we pick something up, invest a lot in it, and then 10 years down the line, we suddenly drop it off the agenda. So I think it's a conversation that we need to have with local authorities, with governments, within the academic community, between the different professions, the material scientists, the economists, the climate change people, and so on.
Thank you, Wendell. You know, I mean, we knew that half an hour was going to be short, and I'm just really conscious of just how short it is. And we've actually run to the end of our time. And I think people are starting to drop off a bit because they have other items in their diaries where that they need to get to. So I'm just going to make some closing remarks. But Wendell, do you have another 5 or 10 minutes? Because I know at least there's
Sure.
one other question in the chat, and I think there might be other people who have questions. So if you can stay
Yes, indeed.
around for a little discussion. I do want to thank everyone and for attending, as well as Wendell, obviously, and Zoe for assisting with the communications. So yes, we did keep the session today short to be able so that people could find time in their diaries, and we're still experimenting with the format, so we'll be grateful for your feedback. For the moment, we're planning monthly seminars, so please do propose topics and speakers and provide any other feedback that you have, and look out for the announcement for a January seminar, which might be by email or on our website or Twitter. So yeah, those of you who have to leave, we wish you a lovely holiday and hope to see you again in the new year. But I hope that some of you can stay and continue this discussion for just a little bit longer. Okay, so
thank you, everyone. Thank you, Julia.
Yeah.
Yep, I'm here.
Yeah, so we've still got, I think besides us, we've still got another 10 or 12 people and there's at least one question in the chat here. Oh, there's several questions in the chat. Does anybody have any hand raising type questions, or shall I read the questions in the chat?
Please do, Julia.
I don't see any hands. Can you see the chat questions, Wendell? But I'll read them.
I can see.
Yeah.
Not quite yet. Okay, if I go to
so
chat.
The first question is, Gaurav is curious about the types of connections being looked into. Is geometry something being looked into, say, along the lines of old Japanese woodworking style joints? So I guess we're talking about sort of inherent connections rather than connection pieces. Is that the gist of it?
That's a really important point. And yes, I mean, the old Japanese connections, because they have an issue with seismicity out there, those connections were actually designed to take quite severe loads under quite, extreme conditions like earthquakes. So actually replicating those joints as far as we can would be very good. Alongside that, anything we can do to exploit, modern advances in manufacturing methods would be good. So for example, I think of 3D printing, which is happening now, and which for some of the materials like the fiber composites they've been using. And one of the nice things about 3D printing is that the geometries that you can cope with are almost limitless. And one of the issues though is that you tend to have to sort of get the material to a pulp and then distribute it using a robot in whatever way you think is appropriate for the application that you're interested in. But yes, I think we should build on the wisdom that is already there rather than pretending that we are starting from scratch, because otherwise there is a danger that we end up reinventing the wheel. So reading around, and of course, quite often architects have a very good handle on the history of development of things like critical connections. So speaking to the architects as well becomes quite important. We learn that way. And by testing out the ideas that the architects come up with, we are in a very good position to actually provide something that people will like and that is structurally robust. So I hope that helps to answer your question.
Thank you, Wendell. There's another question here from Zohir about fiber composites, and I wanted to actually join my question onto this one. So my question was, I understand some of the advantages that you've described about the fiber composites, but I wonder about their end of life. So once, you know, they might be low carbon and easy to maintain and so on, but at end of life, I understand fiber composites to be quite difficult to manage. So that's part one of the question. And the other part of the question is the part from Zahir, which is about, could the use of fiber polymer composites in bridges be extended to pavements or even roads to replace use of bituminous mixtures?
Thank you for the two-part question, Julia. You're quite right. The sort of end-of-life issues for fiber polymer composites is something that's being addressed in the field. One thing people have thought of is sort of burning them to get the sort of energy back. The issue is, you know, there are various issues there that the materials people are probably better qualified to deal with than myself, but certainly it's something that's being worked on. And also, I think, you know, the end of life, there are issues of end of life. There are also issues of end of use. So for example, a fiber polymer composite deck, which has been used in a bridge, if the bridge is dismantled, could actually get reused. So coming back to the circular economy issue in a building. And one of the things with these panels is because they're voided, they're actually very good for use in buildings, because it means that things like services like air conditioning ducts and so on could actually be routed through them. So one of the things we need to develop is a method for assessing the integrity of these units after they've been in use for a while to establish where else they can be used. So it might come for a bridge, and it might not be reusable in another bridge because of the types of loads that you get from lorries, but it may be reusable in a building because the loads are less onerous there. And coming up with standards, coming back to the point that Faye was making, to enable that type of activity will be good. I mean, I know people have started discussing things like barcoding of components before they go out onto site, and using the barcoding and little sensors on there. It should be possible to log the entire service life history of a component made out of, whether it's fiber composites or any other material, especially if it's modular. You know, so, I mean, people have talked about actually using the information from the barcoding method to establish how well a contractor actually uses these and assembles them on site, to what the loading history is, to whether any defects have appeared during the use. And that information combined can actually strongly influence, you know, the future use that the material can be put to. So, you know, in addition to the end of life, I think this idea of the reuse, the circular economy element of it is going to be quite important. Now, I'm coming to the issue of using the units. I think, don't quote me on this, but I do believe that these panels have been used on, where is it? A station in London. It might be London Bridge Station. And some work using sensors was actually done on that within the last 6 or 7 years. So the answer is yes. And I do believe Network Rail have used some of these fiber polymer composite panels for station platforms quite successfully. And it may well be that they have been monitored. That bit I'm not sure of. What I am clear on is that they are being used for these other applications. So people like Network Rail and 1 or 2 key suppliers of these deck units would be able to advise more on that. I'm sure I'll be able to provide some contacts if this is something you'd like to take further.
Yes, and you can, I guess, follow that up with, or Zahir can follow it up with you. I don't see any more questions in the chat. Does anybody have any other questions to raising their hand? There aren't many of us left now. I did want to ask you, Wendel, about the MACE project. And I'm just wondering, because there's still some of you have your bridge testing rig at here east, and I guess there's still some work to be done there. So I'm just in terms of my own sort of getting up to date with the status of the project, but also I guess it may interest others, the continuing work that you're planning to do with that and what MACE intends to do after this.
Yes, that's a good question. Yes, in fact, only in the last 2 weeks I've been speaking to all the people involved. we've actually got a near full scale specimen waiting to be tested in the lab. It's actually located at Brandon, where the 2-story mock-up is. And we basically need it transported to the lab once the proofing of the test rig is done. We hope that all of that can happen latest early in the new year, because that lab testing alongside the work that we've done on the mock-up early this summer will actually give us a more complete picture of the structural integrity of that system, which appears to be quite high. So I think we're going to be confirming what people already know, but it's always good to be able to put numbers to this. There'll be a number of tests that we'll sort of pursue in the lab. And of course, one of the differences between the lab and the field is that we can carefully control the actions that we apply. We can measure them as well as the response. So we can have a sort of direct transfer function between actions and response. When something is out there, temperature changes and so on, even if you can measure them, they're at discrete locations, and then you have to start making assumptions about whether what you've measured applies elsewhere spatially. So I think that is how our lab testing is going to be quite a useful complement to what they've done in practice. So the idea is we're hoping, or we're expecting, that absolute latest by Easter next year, we'll have produced a set of results that Mace and the other project partners can use to design future systems, bearing in mind that this system to a certain extent is still evolving. I mentioned that issues like the connectivity between the panels themselves, the connectivity between the panels and the frame, the steel frame that you build around them to support them. All of these are, concepts that Mace in particular have been developing very nice ideas on and testing. So this whole idea of evolution, whenever you come up with a very good idea, like these cassettes, is something that means we need to keep watching the space for a while.
Yeah, no, it is interesting. Also, I mean, I remember the discussion about the connections, and also in relation to the comment about the Japanese connections. It's clearly somewhere where there can be a lot of inventiveness to make improvements. Thank you. Yeah. Yeah. No, I just wonder if we have any other final questions. I don't think there's anything else in the chat. So Wendel, sorry, did you want to say something additionally? There was a...
No, I was just probably going to repeat the point that I made, was that from the limited work that we've done on, human testing and so on of this, and the analysis we've conducted on them, they look very, structurally sound. So, whatever Macy's plans are, hopefully they are founded on an assessment that reflects that these are very good systems structurally.
Yeah. Oh, Shoma does have a question. Shoma, do you want to reveal yourself?
Oh, hello, Wendel.
Hi, Shoma.
Yeah, it's nice to see you today.
Thank you. The same here.
Yeah. I'm working on design for deconstruction project in the Circular Economy Center, as the same group as Julia belongs. Yeah.
Very good.
My research is like, I think one of the things that you mentioned, the deconstruction of infill walls made by lightweight steel.
Yes.
That is surrounded by the steel frames or concrete frames, and
sure.
We started this April, and we are making progress on this project. And I mean, I don't have any question. I just wanted to introduce myself, and I would like to thank you today. Yeah,
That's excellent. So Shoma, thank you very much, because I think, this is probably also for us the start of a two-way process of communication where we find out more about what happens in the world that Julia is leading, including meeting people like yourself, and that we can invite you to the laboratory. Julia was just asking about a sort of schedule for testing of the MACE units. So at some stage, when we do get it in there, and we hope it's going to be fairly soon, the idea will be to invite Julia's group to come across and have a look both at the test rig and at the specimen in there. I think that's going to be quite revealing. and we can continue to have discussions. It may be that we set up discussion meetings at UCL here East, where the laboratory is based, because they've got quite some nice spaces there. And I think this idea of sort of gradually merging our worlds, you know, the circular economy world and the structural engineering one, will pay rich dividends.
Yeah, that sounds great. Yeah, I'm always happy to discuss this. Circular economy issues with other researchers. Yeah.
That's excellent. Well, you probably have my email address. Please keep in touch. You know, do email me, copied across to Julia, to see how we can develop ideas for, you know, more engagement in the future.
Yeah.
Sure. Yeah. Thank you. Thank you for saying that. Yeah.
Yeah. Thank you both for making that connection, because that's really what these sessions should be about. So that's really excellent. Okay, so I think we've kept you long past your agreed time. So thank you very much for that, Wendel. I think that was an excellent way to start off our seminar series. And thanks to those of you who were able to remain to the end. I hope that we'll see you all in the new year. I guess we're going to be, Lisa, we're going to be, or Zoe, we're going to be posting the recording on the website, will we? So we can also circulate links to that.
Absolutely, yes. Thank you.
Yeah. Okay.
That's perfect. Thank you very much, Julia. Thank you, Lisa. Everyone who attended. Appreciate your time. Hope to hear and see more of you in future.